You're managing a dozen Azure VNets. Each one has a manual route table pointing to a network virtual appliance, an NVA, that acts as your central firewall or gateway. One mistyped next hop IP and suddenly half your cloud is dark. This video is your fix. Stop writing UDRs by hand and let BGP through Azure Route Server do the work. Imagine your company has just expanded from 3 Azure virtual networks to 30. At first, managing routing seemed simple. Every spoke had a route table pointing traffic toward a central network virtual appliance. But as new applications were deployed, new spokes appeared almost every week. Every deployment required another route table update, another manual change, another opportunity for human error. Eventually, routing became one of the biggest operational risks in the environment. The problem wasn't Azure. The problem was relying on manual configuration for something that should be dynamic. In this lesson, you'll learn how user-defined routes solve routing problems, why they eventually become difficult to manage at scale, and how Azure Route Server uses BGP to automate much of that work. By the end of this lesson, you'll be able to create user-defined routes that force traffic through a network virtual appliance, understand how Azure Route Server exchanges routes dynamically using Border Gateway Protocol, and recognize the situations where manual UDRs are still the correct solution. More importantly, you'll understand when Route Server adds real value and when it doesn't. These are the kinds of design decisions enterprise cloud engineers make every day. What you'll walk away able to do. User-defined route, or UDR, is a manual rule that overrides Azure's default system routes. Think of it like a next exit sign you install. When a packet leaves a VM, the subnet's route table checks if there's a UDR matching its destination. If you've got a rule that says 0.0.0.000 next hop virtual appliance at 10.0.1.4, every packet that isn't destined for another address in the VNet gets handed to that NVA instead of going straight to the internet. One crucial detail: the next hop IP must be reachable within the VNet. Cross VNet peering alone doesn't automatically make a remote IP a valid next hop. Enough theory. The actual CLI command that creates a UDR forces the default route through your NVA. Here it is: AZ network route table route create, targeting the 0.0.0.00 prefix, next hop type virtual appliance, and the NVA's private IP. That's it. And keep in mind, the next hop IP must be reachable within the VNet. It can't be a public IP or a remote VNet IP without proper connectivity. Quick recall. Answer the question to cement the UDR basics. Now zoom out to an enterprise hub and spoke. Your hub VNet runs a firewall NVA. Each of your 3 spoke VNets needs a route table containing that same 0.0.0.00 rule pointing to the hub NVA. Every new spoke means another route table, another manual entry. Did someone fat finger a next hop IP? Good luck finding it. This is the spreadsheet approach, and as you scale to 20 spokes, it breaks. There's a better way, and we're about to build it. Quick recall. Let's cement what we just covered. Let's put the 2 approaches side by side. Manual UDRs. The moment you add a subnet or move an NVA, you're chasing drift. Every spoke needs a manual touch. Route Server flips that. It uses BGP, Border Gateway Protocol, the same dynamic routing protocol that runs the internet, to peer directly with your NVA. BGP lets the NVA announce which networks it can reach, and Route Server automatically injects those learned routes into every linked VNet. No ticket queues, no 3 a.m. emergencies because someone forgot a route. The difference is dynamic versus static. Imagine an enterprise with dozens of Azure subscriptions and hundreds of application teams. Every new workload requires routing through a central inspection appliance. With traditional user-defined routes, every deployment requires someone to update route tables manually. That process works when you have a handful of networks. It becomes increasingly difficult as your environment grows. Azure Route Server solves this operational challenge by allowing routing information to be exchanged dynamically. Instead of updating route tables one by one, your network virtual appliance advertises its routes using BGP. Azure automatically distributes those routes throughout the environment. The result is less manual work, fewer configuration errors, and a routing design that scales with the business. That DevOps story in the last scene is exactly the mess Azure Route Server eliminates. Here's the clean version. Your NVA becomes a BGP speaker. It peers directly with a new control plane service, the route server, and advertises prefixes like 10.2 Terraform and 16. Route Server then takes those learned routes and injects them straight into the VNet's underlying route tables. Every spoke subnet instantly knows the next hop is the NVA. No manual UDRs, no ticket queue. And the key thing, data packets never flow through the route server. It's pure control plane. The NVA still inspects every byte. But here's what nobody tells you. Even if you set up route server perfectly and your NVA is advertising a big fat 0.0000 default route, traffic within the same VNet from one subnet to another will completely bypass the NVA. Azure's SDN stack sees a destination inside the VNet and ignores that default route. So if you need east-west inspection inside a single VNet, Route Server alone won't save you. You must still write a UDR. It's the biggest trap people fall into, and now you know it. At the heart of Azure Route Server is Border Gateway Protocol, or BGP. Think of BGP as a conversation between routers. Instead of manually telling every network where to send traffic, routers exchange the networks they know how to reach. In Azure, your network virtual appliance establishes BGP sessions with the two route server instances running in the dedicated route server subnet. Each device identifies itself using an autonomous system number, or ASN. The NVA advertises the prefixes it can reach, such as 10.2.1 or 16. Route Server accepts those advertisements and programs them into Azure's routing infrastructure. Notice something important. Route Server never forwards your application traffic. It only exchanges routing information. The data packets still flow directly through your network virtual appliance. This separation between the control plane and the data plane is one of Azure Route Server's biggest strengths. Pause and test yourself. What did we just learn about the fine print? On an Ubuntu NVA running ExpressRouting, the BGP config is under 10 lines. You define your local ASN, anything but 655 W5, then set up two neighbor statements, one for each route server peer IP, with remote as 6555. Then you advertise the prefixes you want to represent, like the spoke address space. Notice you never touch Azure CLI for routing after this. The NVA speaks BGP, route server listens, and the routes land where they should. That's the entire dynamic side, configured once on the appliance, not repeated in every VNet. Recall. Checkpoint. Did you catch the catch? Proof is on the effective routes blade of a spoke VM's NIC. After the BGP session comes up, you'll see an entry for 10.2.0 16 with two next hop IPs, the active NVA addresses. Those routes didn't come from any UDR you wrote. They were injected dynamically by a route server. No manual step, no drift. If you ever need to verify that Route Server is doing its job, this blade is the first place to look. You've probably noticed something interesting. A virtual machine can have several possible routes to the same destination. So, how does Azure decide which one to use? Azure follows a predictable route selection process. The first rule is called longest prefix match. Imagine Azure has two routes. One route covers 10.0D10.08, another covers 10.1.0.16. If a packet is headed to 10.1.5.20, Azure chooses the 16 route because it's more specific. The most specific destination always wins. If multiple routes match the same destination, Azure then considers where those routes came from. Some routes are created automatically by Azure. Some are learned dynamically through BGP using Azure Route Server. Others are user-defined routes that you created yourself. Azure evaluates these routes using its routing rules to determine the best path for the packet. You don't have to memorize every routing decision. Instead, remember the troubleshooting process. Whenever traffic doesn't follow the path you expected, open the Effective Routes blade for the virtual machine's network interface. It shows the final routing table Azure is using after all route calculations have been completed. Understanding how Azure selects routes is one of the most important skills for designing and troubleshooting enterprise networks. Once you understand route selection, user-defined routes, Azure Route Server, ExpressRoute, VPN Gateway, and Azure Firewall all become much easier to understand. Enterprise networks rarely rely on a single firewall or routing appliance. Instead, they deploy multiple network virtual appliances for redundancy. Azure Route Server can establish BGP sessions with multiple NVAs that advertise the same network prefixes. If one appliance becomes unavailable, Azure can continue using the remaining advertised routes. Depending on your appliance vendor and design, you may also use an internal load balancer in front of the NVAs. That architecture has additional routing considerations and may still require user-defined routes. The important idea is that Route Server automates route distribution, while high availability depends on the overall network architecture you choose. As enterprise networks grow, routing policies become increasingly complex. Not every learned route should be advertised everywhere. Many organizations use BGP communities and route filtering policies to control how routing information is shared between different parts of the network. Exactly how these policies are implemented depends on the capabilities of your network virtual appliance. The important takeaway is that Route Server distributes the routes it learns, while your routing policies determine which routes should be advertised in the first place. Understanding that separation becomes increasingly important as your Azure environment grows. Route Server is a massive step forward, but it doesn't retire the UDR entirely. Spoke-to-spoke and hybrid flows? Yes, Route Server owns those. But the moment you need east-west inspection inside one VNet, you're back to UDRs. Azure Firewall can't speak BGP, so it still demands a manual route. And if your NVA sits in a completely separate VNet without gateway transit enabled on the peering, Route Server won't save you. Write the UDR. It's about knowing which tool fits the traffic pattern. Picture a hub VNet where a firewall NVA peers with on-premises over ExpressRoute. The NVA learns prefixes like 10.1.0.016 via BGP. Without Route Server, you'd have to write a UDR in every spoke pointing to the NVA's internal IP for that prefix. With Route Server, the NVA simply advertises those routes, and Route Server automatically injects them into every spoke's route table. No per-spoke UDR to maintain. When an ExpressRoute circuit fails, BGP withdraws the prefixes, and Route Server instantly removes the route from the spokes. Dynamic failover without a single manual change. Quick reality check. Your network runs Route Server with a third-party NVA, and then corporate security forces you to add Azure Firewall. What's the one step you can't skip? Take a moment. Time to lock in what we just covered. Route Server automates a ton, but one scenario remains stubbornly manual. Test yourself. The numbers don't lie. In a 10-spoke environment, manual UDRs can mean managing dozens of custom routes if you include subnets and prefixes. With Route Server, that number drops to 0. The NVA advertises, and spokes pick up the routes automatically. The potential for drift drops sharply. Changes that take minutes across multiple spoke route tables now propagate in seconds. And high availability support for active NVAs comes built-in, not bolted on. Azure Route Server dramatically reduces the number of user-defined routes required in environments that use BGP-capable network virtual appliances. However, one important exception remains. Azure Firewall does not currently participate in BGP route exchange with Azure Route Server. If your architecture requires traffic to pass through Azure Firewall, you still configure user-defined routes that point traffic toward the firewall's private IP address. This is one of the most common design decisions you'll make when comparing Azure Firewall with third-party network virtual appliances. Whenever you're designing enterprise networking solutions, always verify the latest Azure capabilities, because cloud networking continues to evolve over time. Throw in 100 spoke VNets. In a UDR world, that's hundreds of route tables to update, with change windows and risk of missing one. With Route Server, the security team only touches the NVA. As soon as the NVA advertises the required prefixes, say 10.0.0.12, Route Server injects them into every spoke that allows propagation. When a new spoke spins up, it gets those routes instantly. No ticket, no deployment pipeline, just BGP doing what BGP does best. When things go quiet, it's usually one of three things. First, the BGP session to Route Server won't come up unless the NVA can reach the peer IPs on the standard BGP port. Confirm your NSG allows that traffic, and that the ASN isn't Azure's reserved 6555. Second, if the learned routes never appear in the spoke VM's effective routes, verify that the route table attached to that subnet hasn't disabled gateway route propagation. That switch blocks Route Server's injections too. Third, for traffic within the same VNet, remember Route Server won't push it through the NVA. You still need a UDR if that's required. Open your hub's Route Server in the portal, jump to metrics, and add a metric that reflects BGP peer connectivity, often called BGP peer status. A positive value per peer typically means the sessions are up. Then overlay any advertised and learned route counters. If advertised is correct but learned is 0, the NVA isn't sending prefixes. Double-check its network statements. This dashboard gives you real-time visibility without running a single CLI command, and pinning it saves you from rummaging around during the next outage. Time to lock in what we just covered. Here's the scenario. Route Server is up, BGP peers are green, and traffic flows smoothly through your firewall NVA. Then the compliance team drops a mandate. You must deploy Azure Firewall in the hub. Do you still need to write any UDRs? Think for a second. All right, time to wrap up with actionable steps. You now know how to effortlessly create a UDR manually using the Azure CLI, setting the next hop type to virtual appliance and pointing it at your NVA's private IP. More importantly, you understand when to trust Route Server and when to fall back on UDRs. Configure BGP on your NVA with peer IPs from the Route Server subnet, and you'll eliminate per-spoke route tables. But remember the big exception. Azure Firewall doesn't do BGP, so always write a UDR pointing to its private IP. That's the complete picture. Time to get your hands dirty. Here's a lab you can build in your own Azure subscription right now. I'll even link a Terraform repo in the description that provisions the entire thing. The challenge: deploy 2-spoke VNets, a hub with a Linux NVA running FRR, create a route server, peer BGP, and verify that a ping between spoke VMs actually flows through the NVA. You'll see the hop in traceroute. This is the exact skill that separates someone who just watches videos from someone who can design a network. Go build it. Before you click away, drop a comment below telling us the biggest UDR mess you've ever had to clean up. Every network engineer has that one horror story, a missing route that took down prod, a typo that black-holed half the company. Subscribing keeps you in the loop for the rest of this masterclass. And honestly, the comment section is half the value. See you down there. As your Azure environment expands, automation becomes increasingly valuable. Even if you're using user-defined routes today, it's worth designing your hub network so Azure Route Server can be introduced later without major redesign. For organizations using BGP-capable network virtual appliances, Route Server significantly reduces operational overhead by automating route distribution. For organizations standardizing on Azure Firewall, user-defined routes remain the recommended approach for steering traffic. Choosing the right routing architecture isn't about selecting the newest technology. It's about selecting the approach that best matches your organization's networking, security, and operational requirements. These 4 resources are the backbone of this masterclass. Bookmark them: Microsoft Learn's Route Injection Docs, John Saville's Route Server Deep Dive, Ivan Pepelnjak's hands-on lab notes from ipspace.net, and the Terraform Azure RM Provider reference for Route Server. When you're designing a network and someone asks you to justify Route Server versus UDRs, these are your receipts. One final recall check before we wrap up. Your colleague sees the elegance of Route Server and asks, why not just peer Azure Firewall with it and let BGP do the rest? What's the hard truth you have to tell them? Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.